It is worth going through each type of function one by one and seeing if we can identify any key characteristics of those functions that would allow us to quickly and easily determine the domains of each without having to create a graph. For linear absolute value, polynomial, and exponential functions, we should anticipate that the domain of those functions is going to be all real numbers. None of these functions have a restricting characteristic that would eliminate certain values from the domain. Each one of them is fairly straightforward in their operations. Each one of them is fairly simple in their calculations, and there's nothing really limiting to us. There's no disqualifying numbers. So when we're working with these kinds of functions, we can anticipate that their graphs are going to extend forever left and right. Granted, we may be only interested in certain values, but there's no algebra to be done here. As long as you can convince yourself that a number or any type of number, any type of real number would work when substituted into these functions, then you should have no problem rationalizing the fact that the domain is all the real numbers. Where we run into some issues is those functions where there is some disqualifying characteristic to them. So one of the ones that we looked at in the last video was y equals the square root of x plus 3 minus 1. You could imagine what that would look like if you were to create a table of values and try different values. If x was 1, we would get that y was 1. If x was 6, 6 plus 3 is 9, the square root of 3, we would get y is equal to 2. And we could create a series of values, but we would realize very quickly that there were certain numbers, a large class of numbers, that we wouldn't be able to use. I, for example, could not substitute -5 in. There's just no value there. It's literally incalculable. So the question becomes, how can I find that location without having to just test a bunch of values and see what works and what doesn't? Knowing that this is a square root, and knowing that in order to take the square root of something, that something needs to be positive, that's the fact that we're going to leverage when trying to determine the domain of a function that looks like this. Functions that look like this, and again, this is not about memorizing the graph of these right off the bat. A function that looks like this automatically disqualifies certain values from being used. We need the interior of that radicand, or excuse me, that radical, the radicand, we need it to be non-negative. We can't say positive. We're okay taking the square root of 0. So we need that radicand to be non-negative. Solving this very simple inequality, I get that x is greater than or equal to -3. If I want to write that in interval notation, I'm going to start at -3 and I'm going to go up to infinity. If I want to write it in set notation, I'm going to write it as x is an element of the real numbers such that x is greater than or equal to -3. I know going in that this radical function is going to have limitations. I have to know going in that there are going to be certain numbers disqualified. So I have to know going in that my interval notation and my set notation are not going to be as simple as just all real numbers. We have certain expectations about the way these are going to look. And again, not memorizing it right now, just maybe familiarizing yourself with it a little bit. We have certain expectations about how that's going to look. And this dead space that's over here in the graph is not here for no reason. There's a reason why it's not there. So we want to be comfortable finding that number where the domain is actually going to start. Type of function that we're going to look at is a rational function. A rational function consists of a polynomial over another polynomial. In the case of a rational function, the denominator is not allowed to equal 0. When the denominator equals 0, the function fails to exist, and there's no value for the range. So our responsibility comes in determining those numbers that will make the denominator equal 0. In the case of the two factors that are here, x plus 4 and x plus 2, those two factors will equal 0 when x is equal to -4 and x is equal to -2. The -4 one is very easy to spot. That's the vertical line that was mentioned in the last video that the two parts of the graph never cross. The -2 is a little bit dicier. You might remember in that video where we looked at the graphs, that when I highlighted the point for -2, it said -2 undefined. This line is what we call an asymptote. It is an imaginary line that the two parts of a graph, or in some cases one part of a graph, does not cross. This is called a hole. It is one individual location along a pattern that does not exist given the characteristics of the function. It's called a hole because it is literally a missing spot in the graph. Everything around it is perfectly fine, all the way up to it and all the way after it, but there is that one individual spot where there is a hole. Because x is not allowed to be -4 and x is not allowed to be -2, thanks to the asymptote and the hole, we need to be very careful when we write the set notation and the interval notation for this function. In set notation, we of course are going to be in the real numbers, but we're not going to be -4 or -2. In interval notation, we are good all the way up to -4. We do not include -4. And we are good from right after -4 up to -2, but not including -2. That's where the hole was. And then we are good everything after -2. So calculating the domain becomes an exercise in diligence more than anything else. You know the two numbers that aren't involved in the domain because the denominator is not allowed to be 0. You use those two facts to write the two different versions of the notation so that we can identify where we are allowed to evaluate these functions and where we do have their domain.